Okay, so welcome back everyone to the final session of this week. We have only one talk scheduled for this session, and it's by Arpan Kabiraj from IIT Palakkad, and he will be discussing a finite index subgroup of free group and residual finiteness. Over to you.
Thank you very much. Hope I'm audible. So first I would like to thank the organizers for giving me this opportunity to give this talk, and thank you everybody for attending this talk at least. Okay. So this is part of this work. What I'm going to present today is basically a fun exercise for me and Deblina to do something about this particular property of groups, residual finiteness. So that's the primary motivation, and the goal is to understand what versions of residual finiteness we can define, or what residual finiteness tells us about a group in a more details in some sense. And in today's talk, I'm going to only focus on free groups. So first one, apology, this has nothing to do with Teichmüller theory, at least subject-wise, the topic that I'm going to discuss. But my motivation to study this problem actually comes from the Weil-Petersen geometry of Teichmüller space. So that's the background reason why I started discussing this. So let me start by defining what residual finiteness, just by recalling the definition. So I say a group G is residually finite if given any non-trivial element in G such that G is not equal to identity, there exists a finite group let's call it H, and a homomorphism phi from G to H such that the image of G under this homomorphism is not equal to identity. Okay. So if I take any non-trivial element, I can find a finite group to which I get a map from G to H such that the image of G under phi is non-trivial. This is the same thing saying that you have a normal subgroup in G such that G is not in this normal subgroup. Okay. So that's the definition of residually finite. In fact, you can talk about any residual property, just replace finite by nilpotent group, solvable groups, anything. So this is the definition, and one of the kind of important open conjecture is whether all hyperbolic groups are residually finite or not. That's not known, but free groups are known to be residually finite. It's an old classical result actually, and I'm going to give one proof of that, but I want to say something more. What happens if I try to quantify residual finiteness? So the thing that I want to do is basically, if I start with a free group of n element, I am going to think of it as a fundamental group of bouquet of n circles, let's say, and I will think of normal subgroups as finite covers, and I will try to think elements as words or loops here, and I will see whether the lift exists or not. That's the kind of question that the topological version of the question. So the main question from the topological perspective that I'm focusing is, given any finite cover of a bouquet of n circles, describe all closed curves of gamma which lifts to gamma. So if I just give gamma tilde, if I just give you any finite covering, can you give me a recipe? Now this is kind of, as stated, it's a tautological question, because if you look at the fundamental group of gamma tilde, that's just a subgroup of fundamental group of gamma. So if I give you a subgroup, it basically tells you what are the elements which are there, what are the elements which are not there. So what I am looking for primarily is either a topological description or a combinatorial description of gamma tilde, and from there I can give you a if and only if condition where some element of my free group, which is basically a word in the generator, can be lifted or not. So a refined question from that is the following. Suppose from the other perspective, suppose I fixed one curve on gamma. So that's a element in your free group. That's a word in your free group if you want. Then find out all the cover to which it lifts and find out all the covers to which it does not lift. Can you give me a criteria purely in terms of the word that is given in your free group? Okay. And if we can't do it for all the finite covers, can we find a class of finite covers for which I can answer the question? Okay. So the answer to the theorem that I'm going to answer is primarily this one. I am going to give you a class of finite covers for which if I give you any curve, I can tell you a class of finite covers to which it lifts, and I can give you a class of covers to which it does not lift, which will give you an answer to the residual finiteness for free groups also. Okay. So is the question clear? Yeah. Right. So that's what I'm coming next. So, okay. So let me just give you one thing. So what I'm going to do is I'm going to draw the bouquet of n circle. I will denote it the generators, let's say A1, A2, An, and word will be given in terms of powers of AIs, and the powers of the AI, the indices of the powers will determine if it lifts to a certain cover or not. And the description of the finite cover will also come from exactly by looking at the picture, the topological picture. So the main theorem that we got was actually quite neat. If I give you a cover of, if I give you any curve on a bouquet of n circle, and if I fixed any prime number, then it lifts to at least one of the normal subgroup of index P. In other words, you can write, if I fix any prime number, 2, 3, 5, anything, I can write down the whole free group as a union of finite index normal subgroup of index P. And this union is actually finite. I don't need to take all normal subgroups, I just need a class of normal subgroups. So this is kind of one version of residual finiteness in a refined version of residual finiteness, in the sense that residual finiteness tells us where it does not lift. This is the other way around, where it lifts. Pretty much any indices, if I fix any prime number, it lifts to some one of the normal covers. Okay. And the other version of this is for any given non-trivial curve gamma, this is sort of quantified residual finiteness. There always exists this odd degree normal covering to which it does not lift. In particular, this is residual finiteness. In fact, what we proved is a bit more strong. What we proved is the following. For any element gamma, there will be some integer such that if I take any n greater than equal to m, and n is odd, then this gamma does not lift to any of them. So if for every curve, I get an integer. If you give me any odd integer which is bigger than that number, you can always find a covering of that index where it does not lift. It's like more of a quantified version of residual finiteness. Yeah. In rank of the free group, this P. So I'm talking about non-abelian free groups. Yeah, at least 2 generators. For this one, no, you can get finitely many, I mean, for every given index P, you can create a lot of normal subgroups. Right. So what I'm saying is I don't need all of the normal subgroup in sense. I just need only few of them. Okay, maybe I have said it in a different way. So this union is finite in the sense anyway it's finite, that's not, the thing is for, yeah, so I'm not using all the finite index normal subgroups. I'm only using a particular class of normal subgroups. Not all of them is required actually. Yeah, That's a Marshall-Hall's theorem. That's what he was pointing out here. That's a Hall's theorem. You have a formula which calculates how many normal subgroups are there. Okay. So just to coming back to your question. So first we will kind of denote this bouquet of n circles with different colors. Something like, I'll just give one example, like 3 of them, oriented edges, some particular order, say A1, A2, A3. And then I will describe these classes of covers for which, using which I will be able to show that all these results are true. So I will just denote the generators by A1, A2, An, and all the description of the normal covering will be in terms of A1, A2, An. So before going to general case, I want to give you a particular case, which is what happens if I have only 2 generators, A1 and A2. Let's say AB. Something. Okay. So what I'm going to do is I'm going to look at the combinatorial description of covering of bouquet of n circles, and I will use that to construct my normal covering. So let's see how a L-sheeted normal covering of a bouquet of n circle looks like. So throughout the talk I will fix L to be odd. The only exception where I will give you the example for, so index 2 subgroup, I will tell you how to do that separate. So for the rest of the talk, I will just assume L to be odd. So if I take any finite sheeted covering, it will have the following description. You will have, so we have 1 vertices. If I go to L sheeted covering, you will have L many vertices. Each color will lift to L coloring of edges. And then the in degree edge and the out degree edge of any color has to be 1. That's just the local property of your covering spaces. And then you have to choose a base vertex. That will determine fundamental group with respect to that base. Now because I'm only interested in normal subgroups, the finite covers that we are going to get will be normal covering. So I don't have to bother about this base vertex. Start with any base. Okay, so let's just see the first example, at least for A and B. So let's say this is my free group with 2 generators, A and B. That's F2. And if I give you any word gamma in terms of A and B, which is in F2, I want what happens in index 2 subgroups. How do I construct a covering of index 2 where this gamma lives? And basically, the point is you have to consider only 2 coverings. One is the following. So what you do is, this is an index 2 covering. So you lift A here, come back by A. This is your B, and this is your B. I may be wrong with the orientation, but this is one of the coverings that you consider. The other one is essentially, which is A, and B. Okay. And the point is, if I tell you any element of this group, it lifts to either this one or this one of them. And the reason is the following. Look at any word here and look at any of the generators and their powers. If I fix, let's say this contains at least 1 generator A, and look at the power of the generator A here. Okay. If the power of A is even here, so lift to here. If it's 0, it just stand here, just A square will do this, A to the power 4, and so on. Doesn't matter how whether what is going on with the indices of B. Because B is basically going to repeat whatever vertex you are starting from, whatever power of B is there, it's just going to start and end there. So let's say if I have something like A square, B cube, 3BA, or inverse or something, doesn't matter. Yeah. So what is going to happen is basically you will go like A square, and then B doesn't care, it will just keep on repeating, then you will end up here, B doesn't matter, then A inverse you are going to come back again. So if the indices of A is even here, it will lift to this one. Now the next thing is if the indices of, and okay, so the what I'm saying is this picture I have to take the other two versions also, where you replace A by B, which is this one also you have to take. So this is the other one corresponding to B. So now the thing is, if A has an even order here, then A will lift to here. If B has an even order here, then B will lift to here. Okay? And then the other options that you have is A even, B odd, or both of them are odd. If one of them is even, it's either lifting to this one or this one. One of them is even. The other option is both of them are odd. If both of them are odd, it's lifting to here. Because you can go via A, come back via B. That will give you an even pairing. So every time an indices odd appears for A, you will basically compensate it with an indices of B. So odd plus odd, that will essentially lift to this one. Okay, the argument kind of clear. And so now the generalization of this is try to generalize this picture for N generators and see what are the classes of graphs that you have to consider. What you will change this by, what it will replace this by, and try to get a general formula for that. Okay. And so to that end, let me just specify some notations. So first what I am going to do is I have this vertex, which I will call the center vertex, which I will call the V, and if I have an L index subgroup, in particular L index covering, then I will have L vertices. The vertices I will denote by V1 to VL, which is the p-image of the vertex W or V, or let's say W, because W here. Okay. Then for each J, for each of the generators, so this is my free group now, I will denote the generators by A1, A2, AN. So for each of the generators, if I look at the inverse image of the generators, each edge will give me L different edges, and I will denote them by the same name basically. I will just use the same color if you want. So if this is your, let's say this is my yellow edge, on the covering I will consider all the lifts of yellow edge, I will just denote them by yellow edge. So that you can think of that by color sense, or you can think of them by indices also. I will call this by the same name. And then the other assumption is that I will follow through and through is L is odd number. I will explain why this is there. So suppose I take a closed curve on the free group of N generators, that will be given by a word which is just the power of some generators A1, A2, N and their inverses, and I will consider a reduced word. Although in this discussion it doesn't matter whether you are considering a reduced word or not, end up getting the same answer. Okay. And then the thing that we will put a notation to is that I look at the indices of the power of a particular generators, and I will take the sum. This is not the modulus, just the sum of all the powers of AJ, and that I will consider consider as order of that group, that element with respect to that particular generator. So for example, something like this particular example, this order of A will be 4, B will be 4 also. Just the summation, not the modulus summation, just the. Okay, now let's come to the classes of coverings that we need. This is going to be the most important one primarily. So this kind of takes care of everything. So what is this covering? This is a covering of free group of N element what I'm doing here is, so I have the generators A1 to AN. So let's say I take one generator particularly, which is AU. I take this particular generator, and the covering that I'm going to construct will be an L. So it's an index L subgroup. So it's an index L covering. So for example, this is L equal to 7. So I will have 7 images of the vertex, 3 images of the vertex. And what I'm going to do is only the AU, I'm going to cross 7 times here to get to a loop. Every other generators at each vertex, I'm just taking one copy of them. So in other words, if I'm taking any generator other than AU, I will get a homeomorphic 7 copies. And only for AU, I will get a degree 7 covering of the surface, if you want, degree L covering of the surface. Okay. Description, you have any questions for the description? So this is pretty much the first one, I say. Like A, I'm doing a degree 2 covering, B and B I'm fixing. That's this generalization. So just like our index 2 example, if I look at a word and if I look at the generator AU in that word, if it is there, then what will happen is if this order of AU, the sum of the power indices of the power of AU, if that is congruent to 0 mod L, then that's going to lift here. Doesn't matter what is happening to everything else. Doesn't matter how the word contains any other generator. If it contains the generator AU, just look at the sum of the indices of AU. So if you start from here, where it's a modulus mod L, if it is 0, then basically you are coming back to the same vertex, so the element. If there are some words, some generator words from the other generator, they will just keep on repeating there. It's not going to affect the lift basically. That's the most symmetric picture actually. That's the easiest one. Now, not everything happens to have this property. So where I'm going is I'm looking for a class of finite sheeted example which exhaust all possibilities of a particular word. If I give you an arbitrary word and I look at the way it expressed in terms of the generators, I have to find out a class of covers which exhaust all the possibilities how the word type can be. So this is one such class, which is order of AU is 0 mod L. It's one such class. So there is one group theoretical lemma will be somewhere there, which tells you this covers all. The second one is, let me explain what I'm doing here. This is pretty much same thing here. The thing now I'm doing is, I'm looking at, so let me just focus the picture here. So let's say I take 2 of them, one is AU, one is AV, and now I'm focusing these 2. So the first one I focus only on one generator. Now I'm focusing on the 2 generators, and what I'm doing is, I'm creating a gap when I repeat to the vertex. Okay, and this is where this odd versus even comes into picture. So the point is, because I'm looking at L as odd, I can do it for both the indices. So if I look at, let's say this is a 7 sheeted cover, and this is, if I go to the 3rd vertex, so here I will go to the 3rd vertex, 1, 2, then the 3rd vertex. Then again I will go to 1, 2 and 3rd vertex. We'll do the same thing 1, 2 and 3rd vertex, and then the next one I will reach here, and then the next one again I'm ending up there. Okay, this I can do because it's particularly odd. Yeah. No, I cannot say it for 8. That's the point. This one, this is where I'm actually using the oddness of the odd property. And because for both pair of them, this is a normal covering, so it should be symmetric. First of all, every vertex should look like the other vertex. So I'm not touching any other generators here. I'm only focusing on these 2. And these 2 I'm kind of lifting with a particular gap. So this is not just one covering, this is a class of covering. This K, this is this 3 here. So this class of covering I am denoting by M, U, V and K. This depends on 3 things. First one is it's the generator that you are choosing, U and V, and then it also depends on K, which is from 1 to M, where L is basically 2M minus 1. Minus 1 or 2M plus 1. Anyway. So this is a class of them basically. And again, the lift will be determined by which curve you are choosing. So this is a class of them. Okay. The picture clear? These are the 2 classes only. The other things will be basically tweaking of these pictures. Nothing more than that. So remember this one, you have one picture here and then you replace A by B, you get another picture and the other one is fixed. So this is now this is the first one, the second one is this one. The other things, the other pictures that I am going to show you will be basically I will replace AU by AV and then I will change the direction, that's all. Okay. So in the same picture, I can take AU, do the 2-point gap. So one thing you can look here is I am doing AV here, that's by 3-3 gap. AU is joined consecutively, so the inverse image of AU is connected in that sense. Okay, that's my AMUV, and this is the K denotes the length of the gap in U part. Now, what I can do in this picture is basically swap U and V. I will get another classes of curves where basically AV will be connected and AU will join the first one and the third one and the other one. So that one I call MKUV. So this is MKU of V, that means the first one is connected and the second one is joined by certain gap. MKVU means the AV is connected and AU is joined by the gap. Basically, you have 2 generators, one is connected, one is creating the gap, UV or VU. UV means U is connected, V is creating the gap. VU means V is connected, U is creating the gap. That's the second class of picture here. So these 2 pictures, this is the conjugation relation. If order of gamma of AU is congruent modulo K into order of gamma of AV model, then the element lifts. And this is again like just drawing the picture, if you can see that, like the way we were thinking about is like if I want to start here and I want to end the lift here, let's say, of a word. So what I will do is I will have a lift of AV and let's say a lift of AV and then one lift of AV. Then I'm done. Okay. So that's where this relation comes from. You basically try to see what type of element particularly you lift here, are lifted here, and then get this particular example, just like the previous case. Okay. And again, if I have U and V here, if I replace U by V, I will get the same equation, but now U will be replaced by V. So that's the next one. That's the same thing it happens. You just K become on the other side. You get the same conjugation relation, but now U will be replaced by V. The same picture. Any questions so far? Yeah. So what I'm saying in the sense that, okay, I should have said this in a proper way. When I'm thinking of AU, that's connected in the sense that it connects each vertex to the next one. So AU connects, so let's say, so the first picture AU, if you look at the lift of AU, it connects, if I put an ordering of the vertices, it connects Vi to Vi plus 1 directly without skipping anything, and the V is kind of skipping the thing. That's what I meant to say by connected. Thing, yeah, exactly.
You can just renumber and redraw the picture.
Right.
The
So
picture is
Right, right. So, but the thing is that that's how I'm looking into this picture. So that's the combinatorial description, the background of this picture that I'm using to classify the thing. In this particular way the figure is drawn, I'm fixing one ordering of these vertices, and with respect to, so I should have clarified this. When I'm looking at the lift of the vertices, I'm fixing an order. I'm calling it V1 to Vk. With respect to that ordering, I'm describing this thing.
So as a cover, this MPUV will be the same as M5PU.
Not exactly. So what will happen? If I look at a 7? Yes. Yes, exactly. So that's why I'm going from 0 to M. K is 2M plus 1. If I cross M, I'm going to get the same thing. Yeah. So that's where the oddness is also coming in. Yeah, you're right. Okay. Any other question? Yeah. No. As of now, I'm just odd. No. So this one I'm just describing the covering. That I will need for something else. That I will need for when I try to say, okay, something happens for all the elements, then I need some number theoretic criteria, basically common arithmetic. Okay. So these two are the pictures that are kind of you swap U and V. And then the next set of figures is exactly these two figures. Here the direction of U and V are opposite. The other two figures I will just swap the direction also. So you have two generators. You have two possibilities. AU connects the consecutive vertices, V skips, or V connects the consecutive vertices, A skips. But the directions are different. AU, if I look at the picture here, in that sense, one is clockwise, one is anti-clockwise. The other two pictures, which is I am denoting by NKUV, which is the same picture. Now I have the same direction here. U and V are going in the same direction. Okay. So this is NUV, and then the next one is NVU. So you have this 4-case scenario. You have U and V. U joins consecutive one, V skips, but U and V are in a different direction. And the other possibility is V joins consecutive one, U skips, but U and V are in the same position. So these are the 4 classes. And the 5th one is only one of them joins consecutive one, everything else is. And for these two, NU and NV, you will get this congruent modular relation. Nothing much there. So this is again just writing down how the elements look like. And as you can see, like except U and V, other generators are not going to play a role, because anyway you are starting from any vertex. The other generators are giving you loops there, so that we can just put any number of generators there, you are going to end up there itself. Okay, so now this, let me just kind of, I have written what I was describing in the picture. If I have a closed curve gamma that lifts to the first class, which I'm, so these are the 4 classes that I'm going to consider here. So the MU is the first one, which is like, I'm going to write down just this picture where U connects everything, and then you have MUV where U connects everything and then V kind of skips. Okay, so 1, 2, 3, 4, I need 1. So something like this, and then you have MVU, and this is in a different direction, and the NUV and NVU, this is the same picture with the same direction. So these are my 5 classes of coverings that I'm going to consider, and this lemma tells you what exactly are the descriptions of the curves which lifts to these covers. So first one says that its order of AU has to be congruent 0 modulo L, gamma lifts to MUV, and all these things. Okay. So this gives you a class of coverings for which we can actually exactly determine which curves lift to that, which curves do not lift. Yeah. This is a normal covering. This is finite index normal covering. Oh, that's just, oh, okay. What's the code? Okay. I have no idea. I have some symmetry. I'm not sure. Yeah. For one of them, it's just a Z mod. Yeah. The first one. That's Z mod. The other one, I'm not sure. That one. Okay. So now this is the classes of finite covers for which we can say something. Now comes the algebraic lemma, where I need this odd number to be prime, and which basically tells you that one of these equations has to be satisfied. If I tell you any pair of integers, one of the equations must be true. So if I give you any pair of integers and I give you a prime number, you write p as 2m minus 1, okay, odd prime here. Index 2, we'll deal it separately. So then either A is congruent mod p, B is congruent mod p, or you have the solution of this equation for some x from 1 to m minus 1, or this has a solution for some x belongs to m minus 1. This proof is actually nice. This is a undergraduate algebra problem. Take a pair of integers, one of them must be satisfied. And so, so this is where I'm actually using this prime number p. You will see why. So the proof of this is if you take any pair of integers and one of them is satisfied, you are done. If both of them are non-zero, then this is prime numbers, so you can inverse them a and b, and so you look at the primitive solution of x equal to minus of a inverse b mod p. And if, so p is a prime number, so this GCD is equal to 1. So this solution will be unique. If your solution lies between 1 to m minus 1, then you have this third condition. So I need the solution from x between 1 to m minus 1, because as I said, this covers were created for this key which is 0 to m. That's where this m minus 1 comes into picture. So if the solution exists for 1 to m minus 1, then you are done. If not, then just do a little manipulation. You take the p minus that number, and that should satisfy this. That's it. That's the point. So either x is somewhere between 0 to m minus 1, that will satisfy this equation. If it doesn't satisfy, just take p minus that number. So that will satisfy this one. That's it. Okay. So now how do we kind of complete the proof here? Suppose you start with some curve gamma and this write as word in AI. So choose pair of them u and v. Think of this as generator AU and VB, which is there in gamma. So if gamma is a power of some AU, then actually we don't have to bother much. You can just take a curve where take a covering where you put a vertex and lift everything. You do anything else to the other thing, doesn't matter, it will lift. So I'm assuming that your word at least has two different generators. Power of one generator, then I don't have to do anything. The first picture will do the job for me. So if it has a pair of generators, at least a pair of non-trivial generators from the free group, then you look at the sum of their indices of their power, and I am looking at these two integers, O gamma of AU, O gamma of AV. And now, according to my last lemma, these two pair of integers will satisfy one of these four equations, which is like this four equation. Either this A is congruent to 0 mod P, or you have B is congruent to 0 mod P, or you have the solution of AX plus B equal congruent to 0, mod P is not. So 1 m minus 1, or you have AX is congruent to 0, B. So one of the four equations has to be satisfied. And so now I look into the power. If this is satisfied, the gamma lifts here. That's the if and only if condition. don't bother about anything else. The other one is also true, then it lifts to M of V. You create the class where the generator is AV. Then if none of them are true, then one of the following holds. If none of them are true, then either one of these has to be true. So if the first one is true, that's exactly the relation which tells you that gamma lifts to n of k of u and v. This is exactly the equation which is basically we were using there. If that is not, or one of them based on u and v, you swap them. Either that equation is satisfied and you swap u and v. One of them will be satisfied. And the fourth one is this one. So if either this one will get satisfied or the corresponding u and v you swap, then this will get satisfied. Okay. Right? So what this tells us is the following. In fact, this gives us a little more than that. So now there is another thing that I can focus. This is the next one. Okay. So there is one thing that I want to mention, that this is an if and only if condition, just the first condition itself. If I look at a curve gamma, this gamma lifts to mu if and only if this order of AU is 0. Because it's an if and only if condition, actually tells you how to create a covering to which gamma does not lift, which is the residual finiteness. This line itself gives you the proof of residual finiteness for free. Just this type of covering tells you how to construct a covering to which an element does not. So if you start with any curve gamma, you take a generator from that word representation of the element. Let's say AU is there. If I don't have any now, so suppose I want to prove residual finiteness. So I'll start with a curve gamma in your free group, let's say free group in n generators, and I want to construct a finite covering to which it does not lift. I don't have a bound now on the index. So that means if I take any generator in gamma, let's say there is one generator in gamma which is AU, then if AU lifts to mu, if gamma lifts to mu, then this has to be satisfied. Now you look at the powers of AU in gamma, sum of the powers of gamma, that's a finite number. You take any index which is beyond that number, that is not satisfied. What the first equation is saying, L divides this number, right? So that basically means that L is bounded by that number. That's the first thing. You take a number which is beyond that order of AU, that's not going to divide AU. So that in that covering, this is not going to get lifted. In fact, so this actually, so what, as a corollary of this first thing, you not only get residual finiteness for free group, you actually get in fact more. So what we can prove, so this tells you the following. If I give you any prime number, this works for p equal to 2 also, but let's say I tell you any prime number p equal to 2, I can construct a lift of index p to the power n for some p to the power r for some r to which gamma does not lift. This has a name, this is called residual p finiteness. Free groups are known to be residual p finite also. So this one actually tells you it's residually p finite. This lemma kind of tells you what's the description of an element to be lifted to a finite cover and what also the description of a element not to be lifted to a particular cover from the other perspective. Now that's the results. Now I will ask some of the questions that I have no idea how to answer. I frankly don't know what would be the guess also. So this tells you the following. If I look at the union of normal subgroups, so if I take any prime number p, this tells you that if I look at any normal subgroup of index p, then their union is a free group. Okay, so the first question is, I don't know whether this is true for all integers. If I replace this prime number by any integer, whether this is true or not. So let's say take n equal to, let's say 30. N equal to 30, 20 or 30 or something. Can you write down the free group as a union of index 20 subgroups? Don't know. I have no idea whether it is true or not. That's even for free group, I don't know this is true or not. Second thing is from my perspective that I want to know whether this kind of result is true for the fundamental group of surface. So rather than, this is a fundamental group of a punctured surface. If I replace it by closed surface, that's my original motivation actually. It's residually finite, that we know. Surface groups are residual finite. I'm not sure whether surface groups are residual p finite or not. Try to look for the literature, I have no idea if it's true or not. But in general, can I write fundamental group as the union of any fixed index subgroups? No idea. So from my perspective, what I'm asking is, if I give you a, so if I look at the surface, let's say genus 2 surface, and I look at the, let's say the generators, the other ones also. So that if I look at the neighborhood of the generator, that will give me a free group inside, not exactly inside, but the free group picture inside the surface. For that picture, I can create this lift. Can I somehow close it up? I give you a lift of the covering of the free group. Can I consider, can I extend it? Can I patch up some disk to make it a covering of a surface group? I have no idea whether that is possible or not. Okay. And so this is from my side. The other thing that I'm really interested, just as a fun exercise, can we get a group for which, so let's say I give, so this is 2 parts. Can I construct a group which can be written only as a finite index, union of finite index subgroup of a particular index and not any other index? Okay, so what I'm saying is, if I give you n equal to 3, can you give me a group which can be written only as union of index 3 subgroups, but no other index? It won't work if I take n equal to 4. I don't know whether any such group exists or not. I don't know how to construct any such group. So that's another question. And or you can take any, not just one integer, you can take any sequence of integer and you ask this question. So I have no idea about how to answer this question. So this is, there are more questions than answered. Infinite, yeah, infinite. And also another thing that I am interested in, for which, so for example, if you take 2 residual finite groups and if you take their amalgamated free product, usually they are not residually finite. That kind of, you can construct examples. However, there is a result, I think it's due to Neumann, that if you have some restriction on the group which you are taking the free product, and you are amalgamating over cyclic subgroups, then actually they continue to be residually finite. So I don't know what happens about these properties, these union properties under free products with amalgamation or chain extensions, either one of them. No idea. Okay, so yeah. The questions. So all I have. Thank you.
Any questions, comments?
So this, okay, so this is where I'm, this lemma you see. Right. I don't know, that's what. So that's the result that I have used. If P is prime, ZP is a field. So I can take the inverse of A and B. If it's not congruent to, A is not congruent to 0 mod P, B is not congruent to 0 mod P, I can look at A inverse, B inverse. Here itself I am using that property of prime number. I can solve that in ZP. I may be able to solve it in Zn if n is particular type, but I may not. This is the only place I am using P to be prime number, just to exhaust all the possibilities. Okay. Okay. This union itself is finite. You have only finitely many P index subgroups. No, what I am asking is, like, if I replace Fn by fundamental group of a surface, whether this is true or not. No, for free group, this is true. What I am saying is, if I take fundamental group of a closed surface, whether this is true or not. I know that the second result I know, the residual finiteness I know, fundamental group of surface is residually finite. I don't know whether this is true for free group or not.
Do you know any class of non-prime P's for which this is true, this union?
I don't know pretty much anything about. I tried to search the literature. This is, I mean, this residual P finiteness is there. There are some results, classes of group for which you know residual P finiteness is true, but they are mostly.
Oh no, I mean
for the free group I don't. So again, I'm saying that maybe if I take some integer on which I have control over those equations, for that I can generalize this, but not for arbitrary integer. Arbitrary integers I still don't. And that's just a sufficient condition, that's not necessary.
Any more questions? If there is no question, let's thank the speaker again.